Good morning, dear students. In pre-block elements, we have completed general reasoning questions of group 15, group 16, group 17 and group 18. Group 15, nitrogen family. 16, oxygen family. 17, halogens, and number 18 or 0 group, that is inert gases or noble gases. Now, next part is your chemical reaction. So here, the most important chemical reactions from this chapter belongs to noble gases. Xenon shows some chemical reactions in some special conditions. It means xenon can form compounds. And the most important compounds of xenon are with fluorine, because fluorine is the most electronegative element of the periodic table. Xenon reacts with fluorine and can form XeF2, XeF4 or XeF6. So today we will be going to discuss about hydrolysis reactions of xenon-fluorine compounds. How these fluorides reacts with water. Hydrolysis, breaking down of any compound in presence of water, is called hydrolysis. So here, your first one is hydrolysis of XeF2. XeF2 reacts with water or undergoes hydrolysis, as a result of which we obtain three products. First one is your Xe, then you have HF, and we have O2. So there will be two gases formed, free noble gas, that is xenon, and free oxygen gas, that is O2, with HF, hydrogen fluoride. So stoichiometry, 2 moles of XeF2 reacts with 2 moles of H2O, as a result of which we obtain 2 moles of Xe, 4 moles of HF, and 1 mole of O2. Then we have next one, that is hydrolysis of XeF4. It is a little bit complicated. You have to remember the balancing mole of a reactant side. Then only you can balance the moles on the product side. Otherwise, it is not possible to balance a chemical reaction. And you have to remember the product formed. Product form will not be provided. It will be incomplete reaction. First you have to complete and then you have to balance. So you have to remember the product and you have to remember the balancing mole used on reactant side. Then only it is possible to balance the chemical reaction, complete and balance. So it's a little bit complicated. So when XeF4 reacts with H2O, or when XeF4 undergoes hydrolysis, we obtain two products. Xe, O2 and HF are common to the first one. Here also Xe, O2 and HF. One more compound is there, that is XeO3. Balancing mole 6 and 12, you get 4 moles of Xe, just double of the previous one. Then 2 XeO3, then 24 HF, and then 3 O2. Then the last one, that is the most simplest, XeF6 with water. Hydrolysis of XeF6. It's very simple. Fluorine is monovalent, oxygen is divalent. So one oxygen atom can replace 2 fluorine atoms. So for the replacement of 6 fluorine, we will be requiring 3 oxygen, and 3 oxygen will be provided by 3 H2O molecule. So 3 H2O, 3 oxygen atom will replace 6 fluorine. As a result, we will obtain XeO3 plus 6 HF, all fluorine with hydrogen will form 6 HF. XeF6, this is the complete hydrolysis. All the fluorine atoms are removed by oxygen. This is complete. Now what about incomplete? If XeF6 is made to react with 1 molecule of water, this is incomplete hydrolysis. This is called partial hydrolysis. If it is made to react with 2 molecules, then also it is partial or incomplete. For complete, it requires 3 molecules of water. Now, XeF6 with 2 H2O. Only one way is available. So Two fluorine will be replaced by one oxygen. It will be XeOF4. Two fluorine with two H will form 2HF. Two fluorine with two hydrogen will form 2HF. Now, if it is utilizing two molecules of H2O, there are two oxidants available. 2O with the 4F will form XeO2F2, and here it will be 4HF. About this structure, XeF2, it is having linear structure. Whenever we are having two bonds with three lone pair of electrons, the geometry possible with minimum repulsion is linear geometry. Bond pair will be arranged and lone pair will be arranged in this manner. If we have four bond pairs and two lone pair, the geometry will be square planar. So XeF4 is having square planar geometry. All the 4F at the corners of the square, and one lone pair above the plane, one lone pair below the plane. Then we have geometry for XeF6. If we have 6 fluorine atom and one lone pair, the geometry will be distorted octahedral. The axial bonds above the plane, below the plane will undergo distortion. There will be some repulsion from the lone pair, so these are not axial now. In octahedral, it is always axial, but here it is distorted octahedral. Then we have XeO3. If we have 3 bonds and one lone pair, the geometry is always pyramidal. So for XeO3, the geometry is pyramidal. Now, chemical reactions of chlorine. Chlorine, a non-metallic element, undergoes disproportionation in presence of NaOH. Now, based on the type of NaOH used, product form will be different. You know the meaning of disproportionation when the same substance undergoes oxidation and reduction. So Cl2 in presence of cold and dilute NaOH undergoes disproportionation, as a result of which we obtain NaCl plus NaOCl plus H2O, NaCl sodium chloride. Cl is -1. NaOCl sodium hypochlorite, where Cl is -1. Where Cl is +1. Here it is -1, here it is +1, and here it is 0. From 0 to -1. Reduction, from 0 to +1, oxidation. So in this manner, Cl2 undergoes disproportionation in presence of cold and dilute NaOH. Then Cl2 in presence of hot and concentrated NaOH behaves differently. Cl- is same, NaCl. But here, instead of sodium hypochlorite, we will obtain sodium chlorate, where Cl exhibit OS of +5. So Cl2, where OS of Cl is 0, gets converted to -1. Reduction. Cl0 to +5, oxidation. Balancing moles are changed. Here it will be 3 Cl2, 6 NaOH produces 5 NaCl, 1 mole of NaClO3 and 3 H2. Then about the bleaching property. Chlorine water acts as powerful bleaching agent. Reason is very simple. Chlorine reacts with water and produces HCl plus nascent oxygen, atomic oxygen, which is highly reactive in nature. This oxygen reacts with colored substance and imparts it colorless or makes it colorless. So nascent oxygen with colored substance gets converted to colorless substance. So this nascent oxygen is responsible for the bleaching property of chlorine water. That's all for today. Thank you.